How do I start my thing here? Hold on. All right, so we went through all this weird quantum mechanics stuff, talked about the history of that, the stuff about light, energy, electrons, and we ultimately ended up, if you remember, at this way of describing the behavior of electrons, where they are in the atoms, and they're in these things called orbitals. Okay, so great. That doesn't really tell us a whole lot. It's an interesting theory of what's going on in the atom. So this next chapter is the first part of what are the consequences of that. Now that we know these things about electrons, or we're assuming these things about electrons from quantum theory, what are the actual things that happen, and how can we predict things like chemical reactions or how atoms are going to bond together based on those principles of electrons and orbitals? All right, so the first thing is to look at the periodic table. The periodic table is a way of organizing the elements. We've talked about it a little bit earlier in the semester. We said, the metals are on the left, the nonmetals on the right. We haven't really described this, this structure of the periodic table. The fact that it has kind of a weird shape, that there are these rows and columns, and then the first row only has 2 elements, and then 8, and 8, then 18, then another 18, then 32, and so on. So now we're going to look at kind of what's going on there and what that has to do with electrons. So the first thing we want to think about is what do we do with multi-electron atoms? So the last chapter we only talked about hydrogen. So what happens when you have more than one electron? They go in these orbitals that we just talked about, which means that the electrons can occupy these regions of space probabilistically that we were looking at before. But they have to obey some rules. So the first rule that we want to look at is called the Pauli exclusion principle. And it just says that no 2 electrons can have the same 4 quantum numbers. In an atom. So, for example, let's look at the 1s orbital. In the 1s orbital, what's our n? 0. What's L? If it's a 1s orbital?
I thought you said n can never equal 0.
Oh, you're right. Yes, I'm sorry. N is 1. Sorry, getting ahead of myself. L is 0, because all s orbitals have L equals 0. ML, it's got to be 0. And then MS can be, plus 1/2 or minus 1/2. So let's just pick, and let's say we've got an electron in a 1s orbital that has these 3 and has an MS of plus 1/2. Now let's say we want to put another electron in the 1s orbital. Question is, can we do it or not? So let's call this one electron 1. And then let's have electron 2. So if it's still in the 1s orbital, then its n is still 1, its L is still 0, ML has to be 0. What does MS have to be then? Yeah, it has to be negative 1/2 because there's already an electron in that atom that has an MS of 1/2. What if we wanted to put in a third electron in the 1s orbital? So in the 1s orbital, it would have to be n equals 1, L equals 0, ML equals 0, MS We got a big problem here because ms can only be plus 1/2 and minus 1/2. Those are already taken, so then there can't be a third electron in the 1s orbital. So the 1s orbital can only hold 2 electrons. Sometimes the Pauli exclusion principle is worded in like how many electrons fit in an orbital, but the real language of it is talking about the quantum numbers. The reason that we say that there are 2 electrons per orbital, because as you'll see, this actually holds true for all of the orbitals, that you can't, because of the plus 1/2 minus 1/2 thing, you can only really fit 2 electrons in an orbital. Otherwise, you end up overlapping the same quantum numbers. So from the standpoint of an actual atom, this means that you can have 2 possible electron configurations in the 1s orbital. An electron configuration looks like this, and it tells you something about what orbitals you're talking about and where the electrons are, which orbitals the electrons are in. So in this case, this is the orbital. And this is the number. It's actually not the orbital, it's the sublevel. I should be specific about that because the orbital is talking about the individual one, which for the S there is only 1 orbital in the S sublevel, but like in the P there's 3 and in the D there's 5. So this is technically called the sublevel. So if we wanted to give the electron configuration for a hydrogen atom, we would say it has 1 electron and it goes in the 1s orbital. If we're then looking at the helium atom, how many electrons does a helium atom have? 2. And where can those fit? Yeah, they can both fit in that orbital as we've just said. So the configuration of the helium atom is going to be 1s2, saying that both electrons are in that 1s orbital. Another way of describing this is with a picture. So you'll see this sometimes with boxes or with just a line where they'll show like a picture of an up arrow and a down arrow, indicating the 2 possible spins, up and down, or plus 1/2, minus 1/2. So we say that hydrogen has just 1 electron, so we have the 1 electron in the 1s orbital, and then we have the 2 electrons in the 1s orbital for helium.
What does that say in the box on the second one? 1 what?
What? Those are little arrows. It's an up arrow and a down arrow. So it's like a half arrow up, half arrow down, like that. It's just a visual representation of the electrons. The reason for the half arrow, which depending on the book, sometimes they use whole arrows. Later on in chemistry, it'll become more of a convention that a one-sided arrow means 1 electron and a double-sided regular-looking arrow means 2 electrons. But you can use them either way. You'll see them both ways in these types of diagrams. All right, so what happens now if we get even more electrons? So we have a couple things to deal with here. One thing is what we just talked about, the Pauli exclusion principle. So if we want to have a lithium atom, which is now up to number 3, so 3 electrons, we need to put that 3rd electron somewhere. It needs to occupy an orbital, but it can't occupy the 1s orbital. So it has to find another orbital to occupy. And so.
Wait, doesn't it only have 2 electrons if it's a +1 charge?
But we're not talking about the +1 charge. We're talking about the neutral lithium atom.
Oh, okay, so they're all neutral.
At this point, yeah. We're going to do these for real ions too, but we're just talking about the neutral atoms. So if we have lithium now, we need somewhere for those electrons to go. They can't fit in the 1s, so they have to actually be promoted or put up in a different level, and this level is going to be higher in energy because remember, as the n increases, you have now higher and higher energy. So we're going to bump this one up to the next quantum level and say that that third electron is going to go in the 2s. So it's now going to have 1s2, 2s1, and that second. So what's that last electron, that third electron? What's its set of quantum numbers going to look like? What's its n going to be? Now it's going to be 2 because it's in the 2s, and then L 0 because it's still in the s. It's still an s, so it's 0, and then it's going to have ML 0, and MS can be plus or minus 1/2. So to draw a visual representation of that, we might show now something like this. So we've got the 2 electrons here and then the 1 here.
I have a quick question on
Yeah.
the ML. So if L were to equal 1, then couldn't you give an ML of -1, 0, or 1? Could you
Right. So when we
pick it then?
yes.
Pick one?
Yeah. Yeah.
It doesn't matter.
Well, yeah, the real consequence of no, it doesn't matter. The consequence of that is that when we get into the L equals 1, which is the p orbitals, there's going to be 3 of them that all have L equals 1, but they can have different ML values.
Okay. Oh, okay.
All right, so there's our 3 electrons from lithium. Now, as we keep going up to more and more complicated atoms, we can start thinking about what the energies of these atoms are, or these electrons are, and how that affects other stuff. So one thing that we want to think of is called Coulomb's law, which is just another physics thing that just describes the interaction of charged particles. So what do we know? What do you know about charged particles and how they interact? What repels each other? Yeah, like charges repel each other. And what's the opposite of that? The opposite charges attract. So what do you think those forces look like in an atom? Where are the repelling charges in an atom?
The electrons.
Yeah, the electrons are repelling each other because they're both negative charges. So that's going to become somewhat important. So not only we have this quantum number exclusion thing, but we also want to minimize the repulsion of electrons. If electrons get too close to each other, there's going to be that force there that we want to get rid of if we can. And then where are the attractive forces in an atom? Yeah, the electrons in the nucleus. And so that's a stabilizing force, so we're going to want to maximize that. So do you think that an electron is more stable closer to the nucleus or further away from the nucleus? Yeah, it's stabilized closer because it's going to have that stronger attraction. So then where are the least stable electrons in the atom?
The furthest ones.
Yeah, they're the furthest ones away. So as we go out, we have we go further and further out from the nucleus. We have less and less stability. We have more reactive electrons. So those are going to be the ones that do the chemistry, that do all the stuff. One of the things that we can think about with that is something called shielding. So if we have an atom with a lot of electrons, or just multiple electrons. Let's say we have like a here's our nucleus. Let's say it's a lithium atom. So there's 3 protons in our nucleus. There's 3 plus there. And then we've got our electrons. So the first 2 electrons are in the 1s. They're going to be a little bit closer to the nucleus, but they're going to be approximately the same distance from the nucleus on average. Remember, we don't know the exact distances, but we know that there's 2 electrons that are around the same distance from the nucleus. Yeah.
Does that say 3 plus?
It says 3 plus because there'd be 3 protons in the lithium atom. Okay, and since we know it's a probabilistic thing, we know that these electrons can be anywhere within this particular sphere, let's say. Right. So then that third electron, the 2s electron, is out further because we know that the 2s probability goes out further than the 1s probability. So we would say that this electron experiences shielding. Meaning that the other electrons kind of block some of that nuclear attraction from it. So instead of feeling the pull from a 3 plus charged body, the way those inner electrons would, we might say that that outer electron only really feels a +1 charge because those other electrons are like shielding it. They're kind of blocking some of that pull. They're taking that pull for themselves because they're closer in. And so by the time you get out to that outer one, it's not experiencing as much of a pull. And this idea is going to be really important to a lot of the things that we talk about later in this chapter. We probably won't get to them until Wednesday. But all these effects that we get, like everything from how big an atom is, to how reactive it is, to how easily it's ionized, all of these things are dictated by this idea of the outer electrons being shielded by the inner electrons. Okay, so as we keep counting up, if we continue with what we did here, we keep working on the periodic table, notice that when we jumped from helium to lithium, we had to jump up to the next quantum level. And what happened on the periodic table when we went from helium to lithium? Yeah, we dropped down a level, right? And so that's going to continue. Every time we drop down a level, what do you think is going to happen? Yeah.
On the periodic table.
Yeah.
You drop another.
Yeah, you add another quantum level, another principal quantum level. And actually, if you look on the left-hand side, you might have just thought it was a random numbering scheme, but it actually numbers from 1 to 7. Those are the principal quantum levels of the outermost electrons for that entire row. So we start filling up the 1 level, then the 2, then the 3, then the 4, then the 5, and we follow that along nicely. All right, so then after lithium is beryllium. So we got our 2 electrons here. We had our 1 electron here for lithium. Where do you think that 4th electron goes for beryllium?
2s.
Yeah, right in the 2s, because we know we can fit 2 electrons per orbital before we have to jump up in energy again. And so we would write that electron configuration as 1s2, 2s2. Great. And then we'll jump up to the next one, which is boron. So we put in our 4. Now we got to put in our 5th electron. Where do you think that's going to go?
2p1.
Yeah, it's got to go to a new, different orbital. But now that we're in the level 2, we don't only have an s orbital to put things in. We can also put things in p orbitals. Because in the n equals 2 level, L can also equal 1. So L could be 0 or 1. The L equals 0 was the s. the L equals 1 is the P. So furthermore, because L equals 1 means ML can be -1, 0, or 1, that means we actually have 3 p orbitals. So here's our 2p sublevel, and there are 3 orbitals that we can put electrons in now.
Why does it go right to 2? Oh, because
Because
it's 2, never mind.
Well, p, there's going to be p's in the 3 also, and the 4 and everything else. We'll see that. So we put that 5th electron right there in the 2p. Now, we don't know what the ML value of that electron is. It can be -1, 0, or 1. We don't know what yet. We don't know. We can't figure that out, because remember, it's just arbitrary of how we assign our axes and how we want to keep track of that. So we can say there are 3 orbitals, but we can't necessarily say which one is which. Okay, so now it's time to start talking about some energies. One thing that can be helpful is think about the order that you fill these things up has to do with their energy. We're going to build up from lower energy to higher energy. Excuse me. So our lower energy orbital, our lowest energy orbital was the 1s. Then higher than that was the 2s. Then the 2p's are higher in energy than the 2s a little bit, but all of the 2p's are all at the same energy level. They're all equal, and there's a word for that, which is degenerate. Three degenerate orbitals, which means the same energy. All right. Now that's the 2. So in the 2 level, n can be, or n equals 2 level, L can be 0 or 1. So we've exhausted those 2 possibilities now with all the electrons. So if we get up to the third, so then if we get another electron that doesn't fit in those, we have to move up to the 3rd quantum level. Where we're going to have the 3s and the 3p. And now we can also get the 3d, which has 5 orbitals, because of the now possibility of L equals 2. Okay, so this is the general order of energy. One thing that happens that's weird is that the 4s, because these levels kind of start collapsing as you get higher and higher, the distance between them gets smaller and smaller. And so the 4s actually has about the same energy as the 3d. So in many atoms, so when we start filling this up, we're actually going to fill the 4s before the 3d. It's not quite right to say that the 4s is at lower energy than the 3d. There's some more complicated stuff going on there. But as we'll see, we'll actually fill that one before the 3d. All right, so let's continue on with our ordering, and we'll keep referencing this diagram to help us out as we do that. So to write the electron configuration of boron, we write 1s2, 2s2, 2p1. Notice that we don't separate out the individual p orbitals in the electron configuration. We just say p. So how many electrons total can fit in the p sublevel? 6, because each orbital can hold 2. Right? Each orbital can hold 2. So we can get 6 total. So this number is going to increase from 1 to 6 as we go through the rest of the elements. So let's do that. So after boron, we've got, we'll kind of do them all together. We've got carbon, nitrogen, oxygen, fluorine, and helium. Oops, neon, sorry. All right, so when we get to carbon, we put in our electrons there, and now we have a decision to make. So we've got our 5 electrons for, like boron, and we got to put that 6th electron in there. Do you think that 6th electron goes in the same orbital or in a different orbital? Maybe same, maybe different. So let's think. What?
I know they repel each other.
Yeah. Do electrons attract or repel each other, or don't care about each other? They repel each other. So do you think it's a better idea, assuming the orbitals are the same energy level, would those electrons like to spread out or be pushed together? Probably spread out. Because those p orbitals are all degenerate, they're all at the same level, the same energy level, that means that the electrons can spread out however they want. So the electron configuration for carbon is going to have 2 unpaired electrons rather than 1 pair of electrons. This is not reflected in the electron configuration that we write, because we just write 1s2, 2s2, 2p2. We don't say like 2p0 or 1, 2p1, 1 or something like that. We just put them all in the 2p together. But we should know that those are actually unpaired. So we're going to continue with that same pattern, and that means that electrons don't actually get paired up until oxygen. And that's the first time we're going to see pairing in the 2p. Sorry, I made these way too small. I can't draw on them. And then when we get to neon, they are all filled. And those are electron configurations. Okay. So let's compare this now to the periodic table. How many, if we look at the second row, how many electrons fit in the 2s? Or as 2s sublevel? Just 2, right? And what are the electrons whose outermost electrons are in the, or what are the atoms whose outermost electrons are in the 2s? It's lithium and beryllium. So if you look up the periodic table, you see lithium and beryllium in this nice little block on the left of 2. So for that reason, the first 2 columns of the periodic table are often called the S block. And those are called the S block elements, because all of the elements in those first 2 columns are going to have their outermost electrons in the S. Those are going to fill up the 2 spots in the S. All right, how many electrons did we say fit in the P? 6. And how many elements are between boron and neon? 6, right? So we sometimes call that the P block. These elements in those columns there all have their outermost electrons their highest energy electrons in the p orbitals. So you can tell how many electrons are going to be in the p orbitals just by the position on the periodic table. Fluorine is 1 from the end, so it has all but 1 electron in its p block. And that's going to be the case for all of those rest of those atoms in that column. So the periodic table is organized. The periodic table was made from before any of this kind of stuff was discovered. The periodic table was based on empirical observations. But now we have an underlying theory for that, or a theory underpinning all of that stuff, and it still holds that these things, that these atoms have the same properties because they have the same types of electron configurations in there, especially in their furthest out orbitals. All right. As we continue filling up orbitals, we kind of keep following those same ideas and those same rules until it starts to get weird. What?
That's the theme of today.
That is the theme of today. Everything gets very weird today. So if you look at, and I don't think I have this picture pulled up. See if I can get it real quick here. Let's see if we can find a nice picture of a periodic table that contains the electron configurations. Just because I don't want to have to write them all out here. Science notes. Well, we'll check it and make sure it's right as we look at it here. Okay, let's see, is it right? Okay, it looks good so far. So we're going to zoom in on some of these so you can see it too. I just wanted to check them out. If we look over at that P block, so notice that the electron configurations are given underneath the atom there. And one thing that's a little bit different from what we wrote is you'll notice that there is an element in brackets. What do you think that's all about?
It's the previous
Yeah, it's like the previous noble gas. So instead of writing out, it's not a big deal at the beginning, but instead of writing 1s2, because all of them are always going to start with 1s2, when we get to the second row, we can just write He for helium instead, and that means 1s2 because helium is 1s2. Not a big deal on the second row, but as you get down to the third or fourth row, remember that these elements, like, okay, let's say selenium here, that's got 34 electrons. So if you really want to write the entire electron configuration, you've got to go 1s2, 2s2, 2p6, 3s2, and so on until you build all the way up to the last bit of it. So it's a lot easier if you can just start from argon, which already goes up through 3p6, and then just add on from there. So that's what you see in a lot of these electron configurations. So you'll also see maybe some weird stuff going on. This is over in the P block. The P block pretty much follows the rules pretty well. So you'll notice that, like in this third row, starting with nitrogen, you have 2p3 as the final entry, or you have p3 for the final entry for that entire column. 2p3, 3p3, 4p3, 5p3, 6p3. And that's going to be dependent on that principal quantum number, which is given by the row number. Where things get weird is in the middle. So we had the S block, we had the P block. What do you think the middle is here? The D block, yeah. So these are where we're going to start putting in D electrons, and unfortunately that's where it starts to get a little bit weird. So let's take a look at some of those, and we'll come back to that diagram. So once we get to, let's say, scandium, SC, we're writing our configuration. Let's go all the way from the beginning without using the shorthand, just to practice. So we go 1s2, 2s2, 2p6, 3s2, 3p6. So that's what we would call argon in brackets, because that's the electron configuration of argon. If you ever forget these numbers or you get confused about the counting, remember that the periodic table is right there to help you and remind you. You've got your S block, your P block, 2 in the S block, 6 in the P block. So you can always look there to find those. So what happens after we get to argon? Well, normally if we're just sort of thinking about what comes next, we would go, oh, okay, 1s, 2s, 2p, 3s, 3p, 3d. But instead, let's look at the periodic table and remind us that after argon, we don't get to the D block, we're actually back to the S block with potassium. So we've got potassium and calcium, which are both S block elements, and that gives us a clue that we actually fill that 4s before filling the 3d. So we're going to go 4s2 and then 3d1 to get to scandium. Another thing to remember, we won't get to it today, but when we start talking about ions, electron configuration of ions, the 4s electrons are still going to come out first. So the 4s, even though we fill it first, it still is the highest energy electron. And so those are still going to be the electrons that are ionized first when we take them out. We'll get to that. We'll get to that on Wednesday. All right. So this basically continues as it is. As you might maybe predict, when you get to the F block, anybody see the F block? Yeah, that's going to be these ones down here. Notice the little stars, they actually fit in where those other stars are. So the periodic table should really be kind of like spread apart, so those other ones can fit in. It would just make for a really awkward long thing. That's why they're always done that way. So in this case, what you'd do is you'd be like filling up all of these ones in the 5th row. Then you go to the 6s, 6s1, 6s2, and then you get to the 5d, and then you go down and start filling up the 4s, or 4f. 4f. There are 14 F block, or 14 columns in the F block, because there are 7 F orbitals on the 7 ml numbers in L equals 4 level, 3 level. Yeah.
You do D1 first before you go into F, because
Kind of. So the real answer is it gets weird. And it's not so much weird, it's just that once you get into the D block and into the heavier elements, the distances in energy between the orbitals becomes smaller. So it becomes easier for electrons to jump around from orbital to orbital. So for instance, if we look here in the middle of the D block, you'll notice that it kind of, we start with scandium where we just were. There's our 3D1, 4s2. It's also, so there's different conventions about how to write that. The book always puts the S first and then the D, but you can also put the D first and then the S. So you'll notice that scandium has our 4s2, 3d1 like we just did. Then we add another D, then we add another D, and then when you get to chromium, it actually switches and becomes 4s1, 3d5. And that actually occurs in the next one down as well.
why did I ask this?
But no, this is good. Because what happens is that having a half full shell ends up kind of giving you a special stability because there are no paired electrons in 3d5 4s1. Because each electron gets its own orbital, because there's 5 d orbitals. So each electron gets its own orbital, plus the s1 now becomes its own. So having no repulsion ends up being better, energy-wise, than having the electron up into the d, so the energies kind of cancel each other out, and you get these weird exceptions. So you get an exception halfway through, and you get an exception at the very end, because having a totally full shell is also stable. So when we get to copper, instead of being 4s2, 3d9, it's 4s1, 3d10. So half full and totally full shells give you some special stability. You should know those two because they're really common and important exceptions, copper and chromium. As you get to the 5th and 6th row, the 2nd and 3rd row of transition metals, there are more and more exceptions, and you don't need to know all of those other ones. But those two you should know.
Is 4 then like the highest level you'll get to? 4s, 4e, 4d, 4f? And then I guess there's the g that doesn't.
Right. So in the S, you'll get all the way up to 6, or technically 7 for the radioactive ones, because you're still going to be filling up those higher ones before you go back to the other ones. You'll get to the 4 Fs in this F block, and then the 5 Fs in the actinides, the 2nd F block. But there aren't any, so that if we went then through another round of the whole periodic table, there would have to be an 8th row to start to access any G electrons, which we haven't discovered any of those yet. So that's why we haven't talked about Gs.
Can you go back to the copper and chromium just so you
Mm-hmm. So halfway through, chromium is 3d5. And copper is 3d10. All right. So the last thing we'll talk about today, just to make it a little bit easier, when you write electron configurations or think about electron configurations, you should be able to do it almost directly from the periodic table. You shouldn't have to go 1s2, 2s2, 2p6 every time. So let's look at how that works and how we can do that. So if I told you to write the configuration for bromine, Br. One way to do that is to start at 1 and count it all out and write it all out. But there's an easier way. An easier way is to look at its position in the periodic table, think about what came before it, and write it that way. So we find bromine number 35. We see that it's on the row right below argon. So we're going to start with argon.
Why are we starting with argon?
Because that is the noble gas closest to closest before bromine. It's the end of the row, so we can say we're going to start with that one and then count up from there. So then, again, instead of actually counting up from there, we're going to think about the organization of the periodic table and say, all right, well, after argon, we've got the S block, then we've got the D block, and then we've got the P block, and bromine is the second to last element in the P block. So that means it's going to be a P5 type element. So we're going to write that down. We're going to say, okay, well, we got the S block first, so that's 4s2. Then we've got the D block, and the D block is always from the previous shell. So that's 3d10, because we're going all the way through that D block. And then we're going to be at the 5th member of the P's in the 4th row, which is 4p5.
Can you go over the block names again, please?
Yeah, the S block are the first 2 columns where we're putting electrons in the s orbitals. The P block is the last 6 columns where we're putting electrons in the p orbitals. The D block is the middle, the transition elements that are all labeled with B's on their columns. And then the F blocks are the lambda-9s.
So if you put a D block, you go up 1, right? Like in this machine, you
Yeah.
said 40, you said 3D10.
Right.
I'll
Because
put a D block.
yeah, and then with the F's you go back 2. Because you're going to be, if you think about where the F's come out here, so we're in the 6th row. That means we've got 6S, then 5D, and then 4F coming out there. All right, let's try another one. Let's try nickel. All right, same thing. We're going to say, what was the previous noble gas? Well, it was argon again. So we start with argon. Then we've got the S block, so 4s2. And then we can see that nickel is the 3rd to last in the D block. We know the D block is 10. There's 10 of them. So that means that's going to be number 8. 8, 9, 10. So that's going to be D8. And that's it. That's the configuration.
Wait, so how did you get the S block from that? So you said you went to argon and then you said the S block. What about the other?
Yes, the next one from argon is number 19, which is potassium. And that's in the S block. So you've got 2 S's before you start in with something else. Any questions?
Kind of a question. Why is it 8 as opposed to 6?
Because like counting wise, so it's like 8, 9, 10. So zinc is 10, which is the last one.
I was thinking of the figures. Thank you.
Okay. Another neat shortcut to this, which kind of works. But except for the exceptions, the number of d electrons in the top row is the same as the second digit of its number. So like nickel is 28, and it's d8. Vanadium is 23, so it's d3. You got to be careful again about the exceptions, but that works nicely. Also, 2+ ions are pretty common. So for pretty much all the 2+ ions in the whole transition metals, that's going to be how many d electrons, either 1 through 10, based on those numbers.
So, like for bromine,
Mhm.
again, for example, you have 4s2, 3d10, and 4p5. How can you tell the 4, 3, and 4 from the periodic table?
Okay, so the 4 is because it's in the 4th row. So the row number tells you the principal quantum number for those for S and P. The D is always 1 level behind,
Mm-hmm.
and the F is always 2 levels behind.
The p is always 2 levels behind?
F. The P is always the same level as the S. So if we were to add the P on there, it would be the 4P also.
Okay.
Wait, but. Okay. So then your F would start at 4.
Right. So let's do one that has F before we go. So within the Fs, as you'll see if you look in the book or on that one that we're looking at, it's not real obvious. So like, it's not like you can say for sure that terbium 65 is F 8 because it starts switching around the d electrons and stuff. But we can do ones where they're totally full. So let's do one that's way down there like lead. So lead is number 82. So what's its closest noble gas that's lower than it? Xenon, yeah, for PB, yeah. So that's xenon. All right, so what's after xenon? Well, after xenon is going to be cesium and barium, which is what shell? That's going to be the 6s. Okay, and then we're going to jump down to the F block. So after that 6s, we've got the 4f, and that's going to be all full, so 4f14. Then we're going to jump back up to where the star is there and do the D block. That's the 5d, and that's all full. And then finally, we are going to get to lead, which is the second column of the 6p's. So that's going to be 6p2.
Can you go over that one more time? Like now I'm focused on the number in front of it. How again do you get the number? Like just kind of the top exponent then.
That's how many electrons are in that sublevel. So we've got, and for lead, we know it's in the p block. That's the thing we use in the periodic table for. We find it on the periodic table and we say, that's the p block. That means everything else behind it's going to be full. So we can say, we start with xenon, we fill the 6s, we fill the 4f, we fill the 5d, and then we get however many, 2 more in the 6s, the last couple.
So for F, is it only 4f and 5f?
Yes, it's only 4f and 5f.
So if it's like the first star, it's always going to be 4f, and then the second star
Right.
is 5f.
The second star is 5f,
And so
right?
if it's after the star, it's always like
It's always 14. There's always 14.
The first star is always going to be 4f.
14, yeah. Yep.
I can try.
All right, so keep working on that. So the last thing before we get going, which you've probably heard this before, but we're going to give a term known as the valence electrons. All right, those are going to be all the electrons in the highest n level of an electron. And the core electrons are all the rest. So for lead, we would say that lead has 4 valence electrons because there are 4 electrons in the highest n level, in level 6. And all the rest of the electrons, all the ones in xenon and the F5F or 4F and 5D, we would call the valence electrons, or we would call the core electrons. Sorry. Valence electrons are the outermost. Sometimes those are called the outermost level because we know that the n level also means that they're furthest away from the nucleus.
So there would be 4 valence electrons, 6p2 and 6s2. Is that what you're saying?
Right. So how many valence electrons would be in bromine? 7, right. Yeah. The 4s2 and the 4p5.
So the D and the F's don't matter?
Right. Unless they're the outermost ones. So that's why we don't often talk about valence electrons, at least not in the same way, in the transition metals, the D and F block, because it kind of means something a little bit different. The D electrons do participate in bonding and things, but it works a little bit differently. The reason we make that distinction is because we talked about before with the effective nuclear charge, the outermost electrons are the ones most able to do stuff. So all the things that we care about in chemistry, the connecting and disconnecting and all of that, that's all going to have to do with the valence electrons. And in fact, after this chapter, we're really not going to talk about any of the core electrons anymore. And all the things that we're going to do from this work is all going to be based on the valence electrons, of the outermost electrons. All right. So practice this. Just like anything else, you got to practice the electron configurations to make sure you can do them. Lab tomorrow, the antacid lab, there is no formal pre-lab, but please read the instructions and write to prepare your notebook. You're going to be doing more titrations, so you should be good with that. These titrations are a little bit more useful. You'll actually be like measuring something with the titration. But think about what the experiment entails so that you can work efficiently in lab tomorrow. And I'll see you then.